Well, welcome everyone to GeoHug. So I'm Jess from Prospectors and CoreSafe. So I'm just going to put everyone on mute now. So please stay on mute during the presentation, but please use the chat. And if you have any questions at all, we'll throw some to Erik at the end. But Erik, thank you so much for coming on as our special guest today.
No worries.
So Erik, for the past 3 years, has been the principal consultant at SRK Consulting and has over 20 years experience working in the industry. So I'm really excited to hear with his extensive experience all about modeling and estimation for geometallurgy. So thank you so much.
Yeah, no worries. Thanks for that intro, and thanks, Evan, for warming everybody up. I certainly appreciate it. It's one of those, I've never followed a comic, and so we'll see how we go. All right, I'm going to go share my screen, so bear with me while I get this presentation booted up here. All right, everybody, hopefully you are seeing the title slide for Modeling, Estimation, and Geometallurgy.
Yep.
And from Jess, looks like we are good. All right, well, I'm going to get rolling right into it. So again, thanks for the introduction. We'll get right into it. I'm with SRK Consulting. I'm based in Denver, Colorado, but most of my projects are truly global, worked kind of all around the world. Lately, it's been more North and South America, a bit of projects here and there in Australia, a few other little places here and there. So I want to kind of outline things about what I'm going to be talking about tonight. Just take a look at what goes into modeling, what goes into estimation for geometallurgy. So a good way to start, I imagine if you're tuning in, you've probably at least heard of geometallurgy. It's really an item that's gotten more and more popular over about the last 10, maybe up to 15 years within the global mining industry. So we'll talk about that briefly, some of the benefits, the main value drivers of it, and then really some of the important stuff about how do we actually get it right? How do we actually implement geometallurgy? There's a lot of problems that goes with it. Touch on some of the pitfalls, some of the problems that I commonly see for a variety of commodities and deposits. I've got a number of case histories, excuse me, and so I'll go through those. I might go through a little bit quick, but I'm going to hang around afterwards, and so we can go into more detail, answer questions, whatever you guys want. And then summary and takeaways. So if you zone out for the next 22 minutes or so, at least we'll get those last takeaways for you, and you get something good out of this. All right. So I apologize for the very wordy slide to start things off, but I really think it's important that we all kind of kick stuff off with a clear definition, right? So we all sort of start from the same base, geometallurgy. And apologies, I'm going to read this a little bit on this one. So when I talk about geometallurgy and what is talked about across the industry, when we say terms like geometallurgy, it's really about bringing together the geology aspect, everything around the rocks, basically, along with the estimation and geostatistics properties with metallurgy. And this is really to try to create a model or an ability to predict things that are focused and variables that are focused on processing and recovery for metals. So typically what geometallurgy does is it combines a whole lot of different technical disciplines, commonly geology, mineralogy. We talk about chemical physical assays, everything from density to grade, but also mechanical inputs. So when we start talking about mill, grinding circuits, comminution, making big rocks smaller, potentially pulverizing, looking at different size, granularity of rocks, trying to optimize all those different aspects to basically increase project valuation, NPV, or the revenue from an operation. One of the biggest things with geometallurgy is because it's not a traditional discipline in and of itself, it needs and absolutely requires different disciplines to work together. And you'll see that's kind of a theme that I've got throughout this presentation, is that importance of collaboration. And I call it culture, really that ability for people to work together well across disciplines to really get something good and useful out of it. So with mining, we do it because it's interesting. We do it because it's a job. We do it because it's a business. Ultimately, operations are here, mining's here, mining companies are here to generate revenue. It's super basic stuff, but just kind of as a good reminder to everybody what revenue is, right? It's the volume of mineralized material, times it by the density, the grade, right? The amount of gold, copper, zinc, whatever you're looking at, times the recovery, right? Maybe you only get 80%, maybe you get 55%, whatever it might be, minus all the costs that are associated with getting it out of the ground, getting it processed, beneficiated, whatever it may be, into a final product that can then be sold to customers, sold to market, whatever it may be. So if we take that revenue equation and we break it down into like what disciplines go into it, well, the volume comes from the geologists, right? They do their geologic models and their space, and this is the tons that represent a volume. Physical, density, a lot of times geotechs, geologists, others get involved with this. The grade, that's your straight up assays, right? Laboratory assay work. Recovery, that's the world of the metallurgists. And then all the engineering, how to actually make it get done, logistics, marketing, everything else, that's where the costs come in. So when we look at the revenue equation and we think about, well, what goes into geometallurgy, you're ticking most of the boxes already on revenue, right? And so, you know, obviously this is an important thing that can really move the dial for project valuation. There we go. All right, so some value-added benefits that we see when geometallurgy is done right. As I mentioned before, really trying to optimize, get the most out of revenue and cash flows for an existing operation. The way to do that is to improve the mine planning, right? And scheduling is making sure that things are aligned so that they get to the mill to get the most recovery, so that the blocks or the volumes that contain the most metal, the most value, those get there first from an NPV point of view. You know, being able to predict how your processing, how your beneficiation, how your recovery is going to go in on a quarterly, annual basis, is absolutely key, you know, to be able to extract the most value or the most metal, the most dollars out of your process. If you get it right, you can end up seeing a reduction in stockpiling. So instead of having all these different ore types sitting around here and it's up to a blending group before they put it into the primary crusher, for instance, a little bit of A and a little bit of B and mix some of C in, and all that extra rehandling and the chance of getting it wrong. You know, being able to optimize the blend as well, right? Instead of just relying on, well, a little bit of this and a little bit of that equals something better, we think, we hope. And really to align what's in the ground, the mine, to what the mill needs to do for productivity, as well as reconciliation, right? Measure how well you're doing and then feed that back in to the model and the process. When we start thinking about risks around deposits, right? This could be project risks, risk of not achieving grade, not achieving revenue. It can also be safety risks around potentially deleterious materials, things of that nature. You want to be able to reduce those. So Geomet kind of helps to bring all of that stuff together. So I often get asked this question about, well, you know, Geomet's great, but when do we want to start thinking about it from our project point of view, right? And if you're on an early days greenfields exploration project, you've got a whole lot of other problems that you're thinking about where Geomet is probably a bit down the road. And we see this pretty typical, especially in the junior miner space, the exploration teams out there, they're pretty well focused, but for good reason, right? And so in a case where you're scrounging for financing, you're really trying to hit that next target, to raise more funds, to get more holes in the ground, things like that, I would say a point like that, probably not reasonable to be thinking about Geomet yet. But you want to start thinking about it as reasonable as possible, right? And I like to flag it around that time when a deposit or a company is starting to first report a mineral resource. So this is usually in those early kind of conceptual day study. They put out an MRE or a mineral resource estimate. This is usually before an order of magnitude or a preliminary economic assessment, PEA, is done. Once you start doing a mineral resource, you actually need to start thinking about, from a reporting point of view, no matter what jurisdiction, like an international CRISCO standard, you want to start thinking about, well, what would the recovery be? That's great that you've got a 2 million ounce gold project in the ground, but if you can't recover but 20% of that gold, is it economic? Is it a resource? Like, you know, even early days, these things just at least be thought about. And then obviously, as you progress through a project, and you do more studies, PEA, PFS, FS, so on and so forth, kind of going down the little chart that I have here on the slide, this is where more information should be added from a metallurgical point of view, from a geological point of view, and from a geometallurgical point of view, to the point where once you're at an FS, at a feasibility level study, a geomet model should be feasible, it should be there, and you should be talking about how is the operation going to look at geometallurgy. So, you know, like I said, when people ask, when do we start thinking about what really is reasonable, you know, as early as reasonable, right? As soon as you can. Sometimes you can't. But once you're full operation, you know, there aren't many operations out there that couldn't benefit from some type of geometallurgical modeling or collaboration of those teams. So getting it right, you know, we talk about it being this mix of a few disciplines, geology, metallurgy, mining. But in order to get it right, what's needed is really that combination of both technical and the culture, right? Like, so this little circle diagram thing, it's, you know, you have to have the overlap of these different disciplines and the coordination of these disciplines. But that doesn't work unless you have the right organization, the right culture that really allows for collaboration, right? People to work together for the same goal and easy communication. Not to mention management buy-in, right? Like if management doesn't see value in it, and this could be site management, corporate management, whatever, basically the ones who are controlling the dollars, if they don't see value in it, the whole thing's for naught, right? It's not gonna happen. You're not gonna have support. So when you get different disciplines together, right? Geologists, metallurgists, mining engineers, insert your jokes here, right? And all of them are real, right? Every stereotype is there for a reason, but you have to have that ability for respect and honesty and opening and challenging one another, right? Of the metallurgist challenge geologist of, you know, why did you choose these places to drill, right? And what does this mean from a metallurgical point of view? And the same bit for the mining engineer. You know, you want to deliver information that the mining engineer can use in their schedule that's actually going to optimize, it's going to help, you know, looking at little tiny details that might have been important in exploration, but don't necessarily make their way all the way through mining to move the needle. Well, if it's not important for the mining engineer and the operation, well, the geologist probably shouldn't care about it. So that's what I mean is like, it's really important that these groups talk to each other. Because in order to get it right, you need a lot of time, you need the right people, and you need money, right? And so I talk about money is you need sampling, you need drilling, you need, you know, effort, resources, right? And most of the folks, site geo, site met, site planner, you know, they got other things that they need to do, right? And a lot of sites look at geometallurgy as maybe secondary. And so, you know, whether you have a dedicated personnel on your site for it, or it's something that someone tries to squeeze in, this takes effort, takes time. So there needs to be some dedication. I mentioned before about if it makes a difference for the mine planner, right? So it has to be something that they can schedule, something that's going to matter. If there's a particular mineral that's really interesting for the geologists, but for the Mets, it doesn't matter, right? Like it makes no difference for their recovery. Flotation, it just falls out, nobody cares. You can't have things like that, right? Like the variables that you're modeling, the process of putting it into a block model, it has to make a difference, right? And or else it's lost. So what I've got is for the technical side of geometallurgy is kind of some 5 sort of big key steps that I'll be walking through here. And these 5 steps, I mean, they're really no different from a high level as what you would do for a resource and a reserve model. And that's sample, analyze, model, estimate, and then come up with a plan, right? So unlike what you typically do in a lot of operations where you're focused on a grade variable or maybe a particular mineral, whatever it might be, the geometallurgy variables and the domains, they usually are very different. And usually they're not that well understood, right? Because as soon as a project starts, you're focused on something. Company is a copper gold producer. They want copper gold. And if you start collecting other data, sometimes there's resistance, even within the company for that. And so what typically gets really well understood is these high-grade zones. And these other zones, which you are going to mine as well, moderate grade, low grade, whatever it may be, even problematic zones, they tend not to get as much love, right? Not as much attention, not as much data, so on and so forth. So when we go through a process of, say, doing a resource or reserve estimate, typically it's geologists, resource geologist, maybe geostatistician, sometimes mining engineer, maybe management. You know, a couple people sit down, they kind of walk through these steps, but a lot of times it's within a silo of a discipline, right? A bunch of geos sitting around the table, they'll get it sorted, she'll be right. But each of these steps have to have the collaboration of all those other disciplines, even in the sampling stage, right? Like when the geos are deciding where to put the samples, the Met should be sitting right next to them and saying, hey, that's an area that we're going to be mining. And the mining engineer saying, well, we don't know anything about that area, but that's going to come into our plan in 2 years. Well, we got a 2-year time frame. We need to start understanding that. So those are the things where you start collaborating even down to this level of detail, not just touch base once a year and everything's good and there you go. So the first one was sampling. Typically sampling is the realm of the geologist, right? They'll go out on a hillside, they will drop a rig out there by helicopter if they want to be more dramatic about it, and they'll drill RC, they'll drill diamonds, they'll do their stuff, samples come back, so on and so forth. But when we talk about geomet, we're combining a lot of different types of sampling, right? So diamond is pretty much one of the more common ones, but different diameters, right? So a lot of times InQ, HQ is used for exploration and infill and whatnot. And then PQ, so slightly bigger, will be used for metallurgical drilling, right? Because you need the volume, you need the mass for those larger samples. Sometimes those are twinned. Sometimes you can get assay data on it too. Sometimes you can't. Often what you see at site, especially kind of early days or maybe mid-study level, is some big multi-ton bulk sampling, right? And where you grab big bulk samples, typically right from the surface, right? Probably not representative of the whole ore body, but getting information from something that's 4 or 5 tons can be very valuable, especially about looking at pilot plants and looking at initial feed that from a core point of view, just taking half cores can be difficult, right? And sometimes the Mets are left with dealing with the archived half core that's been sitting in the core shed for the last 5 or 10 years for them to go back and resample, maybe quarter, take the whole darn thing, and something that's been all oxidized and weathered and buggered up and sitting out in the backyard to try to make heads or tails of that, right? And so what happens is you get all this data that has different sources and represent different volumes and were collected in different means, which is where we start to introduce the problems that we see in geometallurgy. Now with operations, we see more and more these days of innovation around sampling. And when I talk about sampling, I'm just talking about collecting data. So we see everything from, say, blast hole data being fed into it, right? Reconciliation data, which is great. It can always be a little problematic or smoothed out, things like that, but actual mill data that can be pulled back and saying, here's a bench, or here's an area of a pit, or an area of underground or a stope. It says, hey, we actually know how that's going to perform. The drill and blast crew, right? They have fragmentation, they have powder factors, they have information about the hardness, discontinuities of a shot on how they need to adjust things. A lot of companies now are dropping more geophysical tools down hole to start to collect data. We can look at things at not only reconciliation of grades and tons of what was delivered to a mill, but how much power it took to actually crush things, right? And so we start to see mining moving into the direction of big data, right? Anything and everything, piece of equipment, it's got a monitor on it, it's collecting data. Well, some of that's useful, some of it's not. And there's a lot of really good information that can be gleaned from multiple points that are collecting data in different ways. So some of the innovations around autonomous drills are a fantastic one. So traditionally, when you looked at blast hole rigs, how fast they drill what the recovery was from the cone for pit sampling and things of that nature. A lot of that could be attributed to the driller. But when you remove the driller out of that mix, so the cowboys who just want to get down on it and make a lot of hole and just plow right through everything, and they wear the bit to death, and they don't care because, you know, that they're getting paid on per meter. When you take the human element out of it and you get consistency across multiple blast holes, now all of a sudden you take a very wide variable out of it, and now you can start taking a look at things like torque and rate of penetration across a whole mine site and understand that, okay, if all these automated drills are optimized, you can now understand factors like hardness, drillability, you know, fractures, soft zones, different materials from something like that, where in the past, a blast hole rig just to put a hole in the ground to be able to throw some ANFO in it, right? So now you start to get some places where you can do this. If all this information from all these different sources can start to feed together, this is where you can start to create those predictive models to understand how well is it going to crush, how much energy is it going to take to break this rock up. Can we actually feed this information back to our drill and blast crews to help them better optimize the work that they're doing? How does this relate to recovery? Not only within the ore zones, but also the waste rock, right? Most mines move more waste than they move of ore, right? At least in an open pit environment, right? Hopefully not underground. But, you know, in an open pit, usually your strip ratio is over 1. So to understand, how do you save money from a drill and blast point of view? Or are there potentially hazardous, deleterious elements, environmentally sensitive materials that are in the waste rock that need to be accounted for or need to be treated differently? Things of that nature. So there's all this great information that can come out of this. So one of the issues that we often see with sampling is the reliability of sampling, the certainty. With sampling and analytical data, you know, a great way to think about it is always garbage in, garbage out. If it's just data that's, we don't know how it was collected and nobody surveyed it and the hole went off to no man's land and what, you can't use it, right? Crap, it's garbage, throw it out, right? Geos kind of live in that world, the quality assurance, quality control, QA/QC world. But when you start bringing other disciplines into this, geotechs, metallurgists, and others, many of them are not as familiar or kind of live and die by the QA/QC standards. So when you start doing representative metallurgical samples, whether it's big bulk or diamond drilling or whatever, to try to bring in some aspects of QA/QC. And it can be absolutely challenging, right? Because a lot of geos have said, well, there's no CRMs, right? There's no certified reference material for these things, or the tests are unique. You know, how do we can't duplicate this. It's impossible, right? But a lot of times, if a second hole is drilled, a twin hole, or if you can actually split your samples for metallurgy, if you can run the occasional blank in there, you know, and people always complain, like, why would I waste money on that? But that can tell you so much, right? All those basic principles of QA/QC can help, if applied through metallurgy, to give you a little bit more confidence or start to understand where there might be some issues with this. So I mentioned before with sampling and some of the problems with dealing with samples of various volumes, right? The NQ skinny little core and somebody cuts it in half and it gets sampled out at 2-meter intervals, or somebody takes a full loader and they just 5 tons, right? And both of those give you one data point. The problem is those two data, they don't represent the same darn thing, right? So understanding that volume variance relationship is really important, and realizing that in some cases, you can't do anything about it, right? So volume variance relationship is just that if you get very, very large samples, the variance of the information that you have in there are going to be a lot skinnier. So I like to use the example, anybody with kids can appreciate this, right? Little kids peeing in a pool, that's what they do, right? And so if you go in with a little teaspoon, I'll take my coffee cup, you go in there and you take some small little sample out of the pool, and you take 40 samples out of the pool, the amount of pee, kid pee, that you're going to get in that is going to vary all over the place. You're going to get a wide spread. Some, whoa, that's way too much in the short end, right? And then in the deep end, yeah, probably not too much. Now, if I come in with a giant bucket, a swimming pool size bucket, and I take 2 big samples of that, I'm going to get a lot less variability. And so you see the same thing with the big bulk samples versus NQ, HQ, PQ, all these other types of sampling things. Now, this becomes a problem later on during estimation, but the key is that understand what those samples might have to do with variance, and then realize that you're not always going to have a perfect situation, that the data can still be useful. But I like to say is take it with a grain of salt, right? There's still good information to get out of that that can be related to one another, but it's not going to be a perfect world. So when we start collecting a lot of different sets of data, drilling, blast holes, in the pit, reconciliation, it can make an absolute mess of your head to try to figure out how do you do this. But if you can take a step back and realize if all these different sources of data are saying similar things for, say, a particular part of a pit or a bench or a rock type or whatever it may be, now you have sort of an internal check and balance on that, right? So if your downhole probe is saying that that rock's hard, and the drillers say that rock's hard, and you've got geotechnical and rock mechanical data that says that rock's hard, guess what? That rock's probably hard, right? And yeah, those data don't necessarily go together, but that's an important piece of information that can be fed back to a model and then used to help inform decisions later on. The next step, analytical. So these are your typical variety of tests, analytical tests, everything from standard chemical analyses, XRF, ICP, so on and so forth, but also benchtop metallurgy, looking at mineralogy, microscopy, looking at small scale comminution. All this information comes into understanding how to pull the geology and the met together. So again, just like the differences in sampling, now you're dealing with the outputs of the sampling. So performing EDA, exploratory data analysis, fancy way of saying really looking at the statistics from both a just straight stat point of view, but also a geostat point of view, the spatial aspects of how these data, what it's telling me about my ore body and different parts of the ore body, right? Because the important thing is 3D, where do these variables sit? So, to assess, understand, and interpret the results, but then also the correlations, right? We talked about hardness. Well, all these things are saying the rock's hard, but why is it hard? Is it silica? Is it the right type of silica? Is it metamorphism? Is it, the list can go on and on. There's a lot of reasons for that. So starting to get somebody who's got a good, say, geostat or stat head on their shoulders to really tear apart this data, look at correlation, start to understand that, hey, every time we have high manganese in the deposit in this area, these are things that we're seeing. So there's got to be a correlation. Now, it's not always as clear as the pictures I'm showing on the screen here, but the top one is just an XY scatter graph of 2 independent variables. Well, there's an obvious direct correlation in there. And then the lower one, where we start looking at ability to crush, or the grindability on blocks, as you move kind of from the north to the southeast of this particular deposit, you see the spatial changes of what's happening across that ore body. And a lot of times these are that interaction of what is the mineralogy telling us, the petrology, as well as the alteration, physical properties of the rock, right? Areas where you've got a rock type that's hard, competent granite that then has been affected by hydrothermal fluids and been altered to clay, and it's just a mess, and you got sulfides in there and all that stuff. That's going to behave so much different in a mill and a crushing situation versus almost something that holds no grade in this case, right? Waste rock and that. And this is one of those parts of the process where remembering the scientific method, everyone putting their science hats on, right? Going back to the basics, is to understand some of these correlations that people may not have looked at before. It's just coming up with a hypothesis, having a justification for that hypothesis, testing it, and then being able to reassess and go back to the drawing board and start over again, right? It's not about getting something stuck in your head about, oh, it's got to be this, or God, these guys have been mining for 50 years. Every time they see whatever, silica in the pit, that means something, right? Well, test it. It's just an assumption, right? And maybe they're right, maybe they're wrong, who knows? But these things need to be understood. And remember, whatever sort of correlations, hypotheses, sort of interpretation that comes out of these, it's good to take that step back and say, does it make any geological sense for this to happen, right? With that picture at the bottom right, with the different colors, is what this grindability is actually doing in this particular deposit. It's showing the degree of contact metamorphism as you actually approach a large intrusive body. So the metamorphism, degree of metamorphism of these rocks are changing the mineralogy, the texture, and the behavior of these to make it basically more difficult to grind as these things have been cooked more. So you go, wait a minute here, that makes perfect geological sense. Maybe there's something to that. So always being able to take it into, this doesn't make any darn sense, is important. So the next step, these kind of 5, is really put it into a model. So there's nothing new and fancy about this, but to create a 3D spatial model, but what you need to do is group things of similar characteristics, similar properties, right? And so in a lot of times, this may not be the geology. This may not be the lithostratigraphy. This may not be something that everybody's accustomed to, is volcanics are over there and metasedimentary is over there and never shall they meet, right? But in some cases, once you add weathering and alteration and the oxidation transition boundary, and you throw a few faults in there, some hydrothermal fluids, some supergene alteration, maybe some other regional metamorphism, and whatever else. Now, all of a sudden, these domains don't really behave like geology, but they become important aspects of geometallurgy that are now grouped together and lumped together. So typically when we see geometallurgical domains, it's usually a combination of a lot of those things I was just talking about. And they can get pretty complicated pretty quick in some cases. So what we see in many times is that once you go back to historic data, the data tends to get worse. Like, not always. Sometimes I go back and I see, people taking amazing notes and people doing a fantastic job. And actually the historic data is better. But in most cases, the further in time you go back, and especially long life operations and deposits, is they tend to be overly focused, right? We're here to mine copper. We looked at copper. That was it. It's like, oh, okay. The other bit is when you start breaking out these different domains, you got to make sure that you don't either oversimplify things and you got black and white, or you've got 5,800 individual little complex things going everywhere. When you start looking at how many samples are in each of your 58 domains and you got 3 samples in each one, well, that's not going to help you, right? So it's always a compromise. Sometimes you have to group, sometimes you have to lump, but you really need to make sure that there's actually samples that are somewhat representative in those domains, and that you've got enough data, a population that can actually tell you something meaningful, statistically significant sample population in that domain. People argue between about 30 and 50 data are pretty good for a domain. That's kind of bare minimum. And that representativity of sampling, a lot of times you figure the domains out as you go, then you drill it, and then you adjust, and then you drill it and you adjust, and that's natural process. When you start looking at older data, a lot of times you see analytical and metallurgical data, the way it's collected, the way it's tested, it changes over time, right? Obviously, detection limits of analytical devices have gotten better over time. Sometimes you go back and you look at arsenic. You might be interested in arsenic, and you go back 20 years and their lower detection limit was 10 ppm, and well, now you care about anything that's between 5 and 10 or over 5. You go, well, that can't help me. So you run into these problems all the time when it comes to modeling. Not to mention, I mentioned before, is that often when you look at where your data is, it's overly focused in the high grade zones. I mean, that can be good. That's where areas that you're obviously concerned with, but future mining, where you're really trying to be predictive of future recoveries, and for geomet, a lot of times that's when you run into issues, right? But again, we follow that process of identifying these, modeling these, and then addressing it, right? More drilling or whatever it might be, and then remodeling it, that iterative process. So the next stage of estimation is where I see a lot of people basically throw their hands up and say, you can't do it. It's too hard. you're mixing data, all the things that you learn in your geostatistics class about implied stationarity, about the rules of sample support and all these other bits. They say, well, you can't do it. And I would not disagree, is that it's not perfect, right? And it may not be robust, but there's certain times that you have to make assumptions or finding data that's useful that you may be able to pull together. And in some cases, you have to get pretty creative, right? So, in most things like grade, where estimation is done, ordinary kriging is kind of the common worldwide accepted practice for interpolation. And actually, it can suit a lot of geometallurgical variables as well, and it actually can work pretty well in some cases. But if you've got very limited data, this is where the creativity needs to come in, right? And this is where sometimes looking at nonlinear estimation, looking at simulation, looking at other ways of trying to get useful information into your blocks, right? Doing nonlinear or looking at simulation, you can now start to get a probabilistic approach, which is fantastic, right? But I would always go back to one of those fundamental things is this something the mining engineer can use, right? And one of the reasons why conditional simulation has not ever really caught on that well is that nobody wants to go to the mining engineer and say, I got 100 realizations here for you. Pick one do you want, right? And it's like, no, they want to know, is it good or is it bad? Is it above a cutoff? Is it below a cutoff? So this is where that collaboration communication is always important. So I wouldn't dismiss estimation right away. And in some cases, you can make certain assumptions on, say, the continuity of variables. It's not right, it's not perfect. You disclose that, right? Obviously, you talk about it. You don't try to hide anything, and realize that it may be flawed, but you have to adjust, and it's something. And so, like I said, this is just more issues with the limited data with estimation, where I say traditional estimation, where people just they say, oh, it doesn't fit ordinary kriging, so throw it out. I always like to think, and this was a good quote from Clayton Deutsch, who said, geostats is for desperate people, right? If all your data fit perfectly and you were just swimming in information, you wouldn't need geostats, right? It's because we have limited data sets and we have problems and we have data that's way over here and way over here, and we need to know what's right here in the middle. So this is where looking at some of those nonlinear techniques, localized uniform conditioning, localized indicator kriging, even things like the radial basis function in Leapfrog, or just other ways of trying to get information to help us make better decisions. And even going to, just making great big blocks and saying, well, we don't really know the details, but here's a 50 by 50 by 50 block that we know the rocks are not going to have that good a recovery in that area. Well, that's better than anything else. Some of the physical properties, if we know the rough means of what, like density is a good example. If we know, all right, you got a granite or you got a rhyolite or something that you kind of know what the mean value is, well, using simple kriging, SK, can help you to try to get an understanding of where things are in that. Where if there's no data, it just goes to the mean, and that's not so bad. The other bit with estimation is sometimes you have to throw your hands up and realize that it has to be a semi-qualitative assessment, meaning you can't necessarily use the data, but what you do is provide a subjective information. So this in case would be providing hardness on a scale of 1 to 5. Simple as that. Like you won't be able to do a detailed hardness because hardness has 5 other variables that feed into it. But what you can tell the mining engineers and what you can tell the mill operators is that this block or this area is a hardness of 1, and that's less hard than the stuff over here, which is at 4, right? And even that information can certainly help. So, getting that general indication of a relative variable magnitude, it can be a helpful place. It's a good place to start. So the last bit of the technical side of here, planning, right? And this is where all that technical work and all that hard work, where that kind of rubber hits the road, where it actually makes a difference, right? So if you can get this information into a mine plan, and you can actually schedule operations and schedule feed and schedule, whether it's stockpiling or whatever, to feed the mill, that's where the value has to be realized. So this is where that importance of getting the mining engineer engaged and making sure it's something they can work with, providing 58 metallurgical variables for them to try to schedule on will easily overcomplicate everything, which means you have an ineffective plan. It's not optimized. It's probably not very cost effective. It takes forever to run, so on and so forth. So, you know, getting something that's useful and it can be done is key, right? And that's kind of the whole point of this. Then if you can do that, you need to start asking yourself, how do we measure this, right? So this is where reconciliation, production reconciliation comes in. The good quote that I always like with reconciliation is you can't manage what you can't measure. So if you can measure the recovery, you can. If you can measure the feed that's coming in, if you can measure the amount of energy that's taking to break up rocks and things like that, like, can you actually create this feedback loop to help improve this whole thing? And that's a key aspect of geometallurgy. It's not just the upfront on the planning side, but it's getting that ingrained within an operation. So there's a lot of different technical pitfalls that come through here, those kind of 5 things. You know, the common ones that I see around a lot of operations is a general lack of data, those unrepresentative samples, you know, no quality control or poor quality control. You know, the met samples, you know, they tend to be very large, so you tend not to get very many of them. It's hard sometimes to understand the details of spatial continuity. Sometimes you just have to make a guess on it and just go with it. But usually if you can draw it back to something geological, you can start to understand where these continuities may go. Those domains are key because those domains that you create, that you model in 3D, are what you estimate into, right? So trying to understand those and realize they're going to change over time. The more data you have, whether it's mining or drilling or sampling data, those will adjust, but you got to start somewhere. And then the estimation side, right? Like a lot of people just kind of throwing their hands up going, I have no idea, but something's better than nothing in a lot of cases. And in some cases, tearing things apart and getting creative with geostats can actually provide a lot of value. Culture. Remember how important culture was, right? Like this is the whole thing. So if you get a problem that has so technically complex across multidisciplines, this is where the team makes a difference. So, I mean, how many folks here who are listening in have worked on tech services teams who, you know, they're like this, right? Where the geo is, they're a rock licker. They just want to be out in the field. Leave me alone. I'm just going to go out and look at rocks all day. And the Met, where's the Met? Well, they're always just staring at the darn bubbles, right? Like they are so focused on one thing, and that's their recovery, and nothing else matters. And the engineer, well, you can always find the engineer because he or she never leaves their desk, right? All they were looking at the computer all day long, probably with headphones on, and they don't talk to anybody. And that's not teamwork, right? And so really the biggest problem that I see is not those technical issues and get hung up on estimation or sampling or whatever, but it's the culture of that teamwork within tech services to be able to communicate with each other, to take what these discipline experts know, bring it together, see the overlap and the benefit, and all try to work toward that same goal. Now, this by far is the hardest part of any operation. And, you know, they call it soft skills or whatever, which is totally wrong. Technical stuff can be worked out. The culture is absolutely the hardest one to get right. All right, so I've got a couple case histories here. Just taking a look at the time. I'll try to go through them here pretty quick. So the first one is in Pilbara iron ore. So some of the problems that we were having, this was a number of years ago, is basically the material that was going on boats that was shipping from the Pilbara up north had really high moisture content. And it was like, wait a minute, where's all this moisture coming from? We're shipping water, right? Like that doesn't make any sense. And we're getting these material that was sticking on belts. It would stick on the back of the truck. You would have carry back, which means you take 50 tons to the crusher and you come back with 20. And you go, whoa, what's going on here? And it just this stuff would stick on everything. The ore would clog up screens, clog up crushers. Basically, whole plants would have to be shut down for half a shift at a time to be fixed. But every time we checked our iron grades, the iron was fantastic. And all the silica and the phos and all the other stuff as well. So what's going on here? We're seeing downtime. We're not making production quotas. What's going on? It was just a logistic nightmare. So a bunch of smart geologists, a bunch of smart metallurgists, combined with the guys from our technical marketing team, they pulled everybody together and said, okay, well, when are we having these issues? Can we trace these issues back to a bench, back to the geology, back to where it came from? So what was going on there? We started going into it and digging more and more and more. And eventually there was a logging code, geologic logging code that was buried way down in there called GOL, ochreous goethite, right? Nice, easy thing to say. So basically what this thing was, it was like clay. It held all the same chemical grades as high grade iron ore, but this thing you could just smush in your hand. I mean, it had no cohesion whatsoever. And if it got a little wet, the whole thing just stuck to everything. And so all of a sudden, now going back through the old logs, finding where these were logged by the geologists, understanding where they are, where were they in the pit, where did we have problems, could we reconcile that back, and start creating a 3D model of where our little problems areas were. And it was like a heat map. And then you start diving deeper and eventually you start to model these things out and start to understand that this is not something you can get from an assay lab, but this is something that you can get from a metallurgical tests, physical property, material characteristic tests. And then once you can identify these and get them into your model, now the mine planners can actually do something about it, right? They can identify these areas that are high, GOL, and things get mixed in, right? Mix the goop with the harder stuff, right? And you can come up with blending strategies. You can come up with, maybe stockpiling it off to the side, or ways of handling it from an engineering output that you can then put it through the mill, and it's not going to bugger everything up. And so it took a lot of time. It took a lot of effort. Some of the data had to be collected. Some of it was already there. But it was one of those things that it was this fantastic collaboration that actually made it work. And to this day, still quite successful. Another example, looking at gold. Now, this is a Carlin type gold deposit in Nevada, where everything there is an oxide-based or oxide gold. So everything was going to heap leach. But it's very simple to get what's called preg rob, right? Material that basically keeps the heap leach from producing the pregnant liquor that's full of the gold to come out of it. So there can be a lot of different things that run into this, but Carlin type deposits are known for being associated with carbon, right? So hydrocarbons, whether it's kind of a seep or whether it's kind of a peat clay type of thing, but also hydrothermal alterations, right? Like low grade epithermal clay alterations, that once those two things can get into a heap leach, not to mention sulfides, will just ruin the recovery of your heap leach, right? And in deposits where there's a lot of faulting, a lot of folding, and that oxide sulfide boundary is not just a straight sort of weathering boundary, but it's all over the place. You really need to understand this. This one particular deposit, they had some issues with microcrystalline silica. There was also some barite in there that a combination of all these things would reduce recoveries and just some problems. So ensuring that you got the right ore to the heap leach was absolutely critical, and it was so easy to stuff it up. So it was a case like this where they had traditionally just focused on gold. Where is gold and where is it not? And their assay sheets were nice and simple. It had one variable on it, AU. And so when you start pulling it all together, you start to realize, God, we need more information. And so additional drilling, focused logging, different characterization of all these deleterious elements, understanding where carbon is, where it is, and so on and so forth. And that took a combination of the Mets and the geologists to kind of go back to the drawing board, pull all this together. And then once you had that in a model, then it was up to the ore control geologists. It was up to the mining engineers, the short-term planners, to really design their shots to try to best optimize this so that they weren't mixing a lot of sulfide in there. They weren't mixing carbon, that these things could be segregated and kept separate so that what went on the heap leach actually gave the heap leach performance the best. Because once you screw up a heap leach, forget about it. It's an absolute mess to try to fix it. Next one that we've got, this is a copper gold porphyry system. So in copper copper gold porphyry systems, you often see things like gypsum and anhydrite as well as fluorine, that once those things get into the flotation cell, all hell breaks loose, right? And it just reduces recovery, right? And so trying to understand where these things are can be a challenge, to say the least. Gypsum and anhydrite, I mean, a lot of times these are little tiny stringer veinlets that go every which direction. And sometimes you get fluorine in places you're not expecting it, so on and so forth. So not just focusing on where's the copper, where's the gold, or any other type of major key economic variable, but these little tiny kind of annoying deleterious minerals that can make material changes to the recovery. Arsenic was an issue in this particular deposit as well. So once you, there were zones of the ore body that were high arsenic. Once that kind of made it in, it did get concentrated up and with the metals. And so your concentrate now is subject to penalty because of too high of arsenic. And so really trying to understand, how do we come up with a plan to mine these zones so that the blending is optimized to keep our arsenic low, or to identify zones of high anhydrite gypsum. And what made this even more complicated was a block cave, right? And so you're underground. Once that block cave gets developed, you have to maintain a certain draw point mining rate to keep that cave moving, right? And so you can't just go, I'm going to ignore everything over on the west side because that's all high arsenic, and just mine the goodies over here. Your cave is not going to propagate properly. You're going to lose part of your reserve and make a big mess for your shareholders and everybody else. And this isn't something you can go back and drill into as well. Once it's established block cave, it makes it hard. So, you know, this is one of those where the geologists, the metallurgists, again, get back together, sit down at a table, trying to understand, what are those key thresholds? What can we put in? What can we blend out? You know, this is one that we went back through all the old exploration logs, the drilling logs, and anytime there was an occurrence of gypsum and hydrite, a fluorine occurrence. So this is subjective geologic logging, right? Someone says, a little bit, a lot bit. What does that mean, right? But they saw something. There was a presence. It wasn't quantitative. You didn't have 0.00, you know, ppm, whatever, but you had relative size. So now all of a sudden you could take that relative information spatially, put it back into the model, and at least identify zones of the fluorine that were causing potential problems. And then you start looking at the correlations of those. Oh, well, that only seems to come in during this type of alteration event. Oh, I bet we see it in other places too. And you start to get the idea of how this goes through. So, you know, eventually a draw point strategy mining could be devised to help minimize a lot of slugs of high arsenic, a lot of slugs of these things. It's always a balancing act, but once it's in the model, the mining engineers can then try to handle it and work their magic to try to get something out. One more on here. This is a magnetite iron ore. This is in North America. So banded iron, magnetite iron ore. This is one where one of their big economic drivers of whether they decide it's ore or waste, because it's so consistent on grade, is actually how hard this rock is, right? The grindability of this thing. So trying to understand, this was actually a picture I showed earlier on, so you guys kind of got a preview on this one. But, you know, taking a look at all these different multiple inputs about degrees of metamorphism, the different strata that's in here, looking at the iron content, the silica content, looking at faulting, alterations, all these other things to try to understand, well, where are these things just really, really hard, and therefore it takes too much energy to actually break these darn things down or causes problems in the mill. And so, you know, getting information together, and again, the Met sitting down with the geologists, and in this case, rock mechanics and geotech engineers, to try to understand how can we actually create a map of this ore body in 3D to look at grindability. And so this was a lot of data crunching, a lot of looking at correlations, a lot of looking at that spatial exploratory data analysis, or EDA, to really try to understand how are these different strata, these sort of you know, layer cake strata, how are they behaving when they're near metamorphism? What about when they're near structure? What about when they're near near surface supergene alterations and things like that? And so, you know, once you start pulling all this stuff together, you can really start to help the mine planners to create a better plan, instead of all down in, you know, 2 or 3 open faces in one part of the pit where everything is hard as can be. they can start spreading out their short-term plan and have a blending strategy to get a more amenable product that gets to the mill. The last case history, this is industrial minerals. And I wanted to include this one because a lot of times folks in industrial minerals, the term metallurgy doesn't exist, right? They say, well, we mine minerals. We don't actually mine metals. It's the same darn thing, but they call it processing, right? But it is the metallurgy. And actually, there's a lot of cases where geometallurgy, maybe not the term, but the philosophy of it can be very, very beneficial for some of these industrial minerals and niche deposits. So this particular one, there was an older mine, and it was starting to run out of basically the highest value mineral. So this was a very pure talc that could be used in high-end polymers and paints and had a huge margin. The problem is that the mine had been traditionally focused on that. All the customers were focused on that. And as you got deeper in the ore body, that stuff started to run out. And so it was about aligning the marketing with mine planning to say, look, geologists and resources say this is what we have in the ground, but we're trying to sell something else, right? And our processing is set up for something else. So how do we sort of update everything? So getting the process folks, the geologists, the mining engineers, and with the R&D guys, the marketing guys, to say, look, this is actually where we're going. How can we maybe beneficiate this stuff to still keep up with demand for that older, really high value stuff? But also, can we explore new markets for this that might be lower margin, but we're not wasting it, right? We're still seeing a positive value coming in. There were also some deleterious materials with some association of fibers that were out near, not in the ore body, but associated near it, and some zones of higher arsenic. And because we were talking about beneficiation from flotation and some other stuff. And so this is one of those that just getting all these guys in one room, a lot of times never talk to each other, actually saved some of the mine life here, where we were able to change the strategy of what was being sold by optimizing it to what's actually in the ground. Sounds pretty easy, hard thing to do. All right, I'm almost here at the end with a summary and takeaways. So I hope you pulled a few things out of this that maybe you've seen in your day-to-day work at your operations or some of the places that you've worked. But, you know, geometallurgy, it's not easy. There's a lot of complications. You have to be flexible. A lot of cases, you've got to spend money. This is what I'm saying. It's not cheap. You got to spend money for the analysis. You got to spend money for the drilling and the assessment and the work that actually takes to get done. But when it's done well, the benefits way outweigh what those costs are up front. That's for sure. I keep harping on the culture and that collaboration. It's absolutely key. You know, we all become technical niche experts within our discipline, and then we don't necessarily appreciate and understand the challenges that other disciplines have until we sit down and start talking to them about common problems and realizing that somebody at the table probably has the answer. You just don't know it yet because they kind of work in a different silo. So you have to be creative, you have to be flexible, you have to realize that even a partial solution is better than ignoring a problem. So when I talked about all the issues with like estimation and people getting kind of caught up on things, is that even if it's sort of something, that's better than just saying, hey, it doesn't exist, fingers in the ears, walk away, right? So, you know, if you're looking for, you know, organizational geomet support, like being able to actually get a geomet program to go, and support from corporate, support from management, to say, look, there's value in this. Always start with a cost benefit analysis. Really start looking at where's our lost revenue, where's our downtime, how, you know, are we able to bump up a couple % on our recovery? So these minor changes in recovery can equal big dollar values when you start multiplying it by annual or quarter production. So when you compare that, what you could get out of it with the cost of drilling and analyses and doing the modeling and these other bits, a lot of times it's small dollar amounts, right? So, you know, that cost benefit analysis of that comparison to management of like, if we spend a little, we can get a lot. That's where you start to get that, that buy-in. And when you're starting to pull these things together, make sure every team member has a voice. You never want to try to just have, say, the Mets try to approach a geomet project, because without the support of the mining engineers and the geologists and everybody else, it's going to fall down. So it's got to be collaborative, even from day one. And a lot of times when you get into these complicated situations, bring in those specialists, right? There's probably, if you're in a larger organization, fortunate enough to be with a big mining company, there's probably some corporate people who are maybe at other operations or at headquarters or whatever that can be brought in to help understand some of these problems. There's always the expert consultants if you don't know how to do geostats, or you know what I mean? There's these experts that you can bring in on extractive metallurgy. Don't be afraid to include those in there, because having another set of eyes come in can make a huge bit of difference to help push over a certain hurdle at times. I think that's all I've got. Yep, that's it. Thank you everybody for your time. Let's see, I'm at an hour. Oh my goodness, look at this. I'm actually doing pretty good here. Jess, maybe I'll hand the puck back over to you.
For sure. Well, thank you so much for that. We have had pretty active chat room going on. So I'll just scroll back up to the top. As a professional, how many feasibility studies you've seen which were based on the 4D geological geomet model?
How many feasibility studies have I seen on a geomet model? Not enough would be my answer. I wish I saw more. You see it more and more common these days. Probably within the last few years, you know, I've probably been involved with maybe 5 feasibility studies, and I would say most of them had geomet models. Maybe 1 or 2 did not. It's also a product of how complicated the ore body can be, I find in some cases, where people fall into the geomet world out of necessity, right? They say the mother of invention or innovation is desperation, right? And so if you're dealing with an ore body that's maybe marginal on grade or costs or whatever it might be, you have to be smart about it. You have to go after it. So these ones that are maybe junior companies, mid-tier companies, ones that aren't considered world-class tier 1 deposits, they get really good at doing geomet because they have to. Hopefully that helps answer that.
I'd be interested to hear more about how you can use downhole geophysical data in geomet work.
Yeah, okay. So downhole geophysics, you know, the stuff that I've been involved with downhole geophysics could be things like gamma density, which is a fantastic one to collect a lot of density across a large area. Looking at things like clay zones, looking at shale zones, looking at radiometrics. For instance, if you got high potassium from downhole radiometrics, that can show you where maybe you've got clay alterations coming in. Resistivity is another one that can show you some information. It really kind of depends on the commodity type, the deposit type, the mineralogy, and the rocks that you have there. Now, geophysics is not a direct measure of rock, right? It's not a piece of core that you can physically grab and touch and sample and break up and do whatever. But what it can allow you to do is collect a lot of data over a very extensive area for cheaper. And if those can be calibrated using real data, so I'll use the gamma density, right? Like I can go out and drill a dozen core holes across some various domains and get a good idea on some intervals of what density does over there. But then I can go to my other 300 holes that are maybe shallow RC, and I can drop gamma density down the whole darn thing at a fraction of the cost. Now I can pull all those together where there's twin holes or where they're across a domain and see correlations. Now they don't always tend to be exactly the same, but usually there's an adjustment. And once you can get enough data and you can get confidence in that, now you can apply the outcomes from that geophysical downhole tool to maybe a whole domain or to a whole deposit at a lot more reduced cost than drilling a bunch of core holes. So switching from core to RC, using downhole tools, things of that nature. So it's very much a supplement. It can't be done just by itself, right? So there has to be that quality control aspect of it. It has to be calibrated. It has to be rooted in reality, right? And but there's a lot of cases out there where it can be used quite well.
How will the geomet variables be reported, such as hardness, especially if we had a different rock types within the block or the mineralization zone?
So a lot of times it doesn't, like when you say reporting, I'm assuming you mean like mineral resource reporting or public reporting. A lot of times it doesn't actually make it that far, but it's more of an iterative step that helps in the mine planning stage. When you're disclosing, say, mineral resources, it's usually key economic variables of grade, density, and if there's something that's significant on the deleterious side, sometimes that's reported, but a lot of times it's at the discretion of the QP. But these other internal variables, like say hardness, or I was using the gypsum anhydrite, for instance, those are things that would get coded within your block model. And then if you have a recovery assumption based on the degree of those type of variables that go in there, then that can be coded in, and you can start coming up with calculated variables or variables that come off of, say, a regression, saying that, okay, well, we know from all of our data, if you have X amount of anhydrite gypsum, your recovery drops so much, apply that to your copper, now you see how much copper you get out. Now you have a new value, dollar value for that block. That can then be scheduled, right? So a lot of these don't actually kick out as far as a mineral resource, but they're used within the mine planning scheme to either come up with a dollar valuation or a blending strategy or a way to try to mitigate risks, reduce risks, or to optimize areas where the recovery might be improved.
How many samples or composites should be selected at each step of the study phases? I guess the volume variance relationship should play a big role, more variance, more samples, but does it exist scientific relation to calculate the number of samples based on a precision accuracy target?
Oof, I'm not sure I can answer that one. I should have grabbed a beer for that one. It's a great question. I'd probably default to people who are a lot smarter than me on that one. I hate to give the answer, but it depends. A lot of times, if you can get down to a domain that is reasonable, is relatively stationary, meaning that that mean value doesn't vary very much within that domain, the variance is relatively understood. I mean, you start getting quite theoretical on these things versus reality, where Mother Nature tends not to behave that well in these cases. I'm not sure there's anything ideal. It usually comes down to working smart with the data you have, right? And being able to make the most out of what limited information we have through drilling or production or whatever it might be. Good question. I wish I had a better answer. I'm sorry.
Yeah, Joe had a lot of comments about that sort of stuff as well. So like every property of the ore body you care to think of is function of geology, mineralogy, and chemistry, and it all tells you something about the ore body. So no data is useless.
Yeah. I mean, I've seen some data that came pretty damn close to useless before too, but that's a whole nother reason. But no, you're absolutely right, because at the end of the day, our business is about finding rocks that have value, right? Somebody's willing to buy it, the metal in it or the actual mineral or whatever. So our job is to figure out how to get it out of the ground, how to make it from big to small and in a form that people are going to buy it at the cheapest price possible. So the connecting thing of the whole thing is rocks, right? Like everybody who deals with mining, they touch rocks at some point, right? You might sit in a corporate office and never actually see a bloody rock, but that's something in there. So if you're collecting information on the physical, chemical, material properties of the rocks in and around your deposit or ore body, any of that information that's being done can be useful to somebody, and it can be difficult to extract the value out of that, but a lot of times if you can combine it with other pieces of information, other pieces of data from other disciplines, now all of a sudden it starts to paint a picture. And that's what I was saying, is like the quality control and not necessarily being able to run your traditional standards and blanks and duplicates and all that stuff, but having other data from other sources that agree with what your conclusions are for these different parts of the ore body, these different parts of domains, are in some cases about as good as you're going to get for quality control. When nothing jives, that's where you know you've got a problem, right? Either the data is not worth anything, or the complexity is so much that you don't understand it. And usually if that's the case, that's a big flag for you to go and say, we need to understand this. If it's, obviously part of your body and contains grade, that you need more money into this, you need tighter space drilling, you need whatever it is, full geomet program.
Aren't penalty elements assayed as a matter of course?
You would think so. In most cases, yes. In most cases, they are. Looking at copper concentrate, for instance. Usually the buyer goes through an analytical process. The seller goes through an analytical process. They both go through and they analyze a vast quantity of potentially deleterious elements on whether they meet a threshold for penalties, or maybe there's extra silver in there and you get some credits, or whatever it might be. But that being said, I don't think that's the part of the value stream where you want to have your data being collected, right? You want to have that data on deleterious elements collected before it gets to the mill, before it gets to the con. Where, you know what I'm saying, is that if you can control these things through other strategies, through your operation, that's when you can add the value. If you get these high values from the con, that should absolutely be part of your reconciliation. That can then feed back in to say, hey, our con had high, whatever it was, right? The manganese was there. So where did that con come from? Can we pull it back to a spatial location in the pit or a time period? Where did we mine then? And that doesn't always work, right? Because of blending and mixing and all that stuff. But that information can certainly be valuable in understanding, trying to bring it back into a spatial area of what's happening in the ore body.
In the process of estimating the ore grades, it has great influence, the identified 3D domains as well as the impact of the structural models. Currently, what impact do structural models have on determining geometallurgical models?
The structure can be absolutely key, right? Structures tend to be the pathways of fluid flow, right? Pathways of fluid flow is where you see alteration and mineralization in many cases. Depending on the age and the details of your body, those pathways may no longer be existent if it's, some greenstone, orogenic gold type of thing. But those pathways could have meteoric waters or hydrothermal waters coming through there where you get increased supergene alteration, where you get weathering, where you're getting oxidation of minerals, or clay ingress, fault gouge. The list goes on and on and on. Or even like late stage, say mafic, diabase, dolerite dikes that shoot through and dilute everything, right? So understanding structure is absolutely key. I probably didn't mention geotechs and structural geologists as much as I probably should in a presentation like this. But when you're coming up with your domains, understanding that interaction of geology, lithology with the structure, those alteration types is absolutely key. Personally, when doing these models, I always start with structure. Really, is create that as the skeleton framework, really. If everything hinges on that. Once you get your structure kind of figured out, the folding and the faulting, then if you can understand lithologies, whether it's strata, whether it's intrusives, whatever, and then it kind of goes from there, and it starts to make sense after a while. So yeah, structure is absolutely key to sorting out those geometallurgical domains in almost every case I've seen, honestly.
How many complete working geomet models have you seen being used for mine planning and reconciled to plant performance?
I've seen a lot of them. The reconciliation can be a challenge. Reconciliation is a challenge on any day, right? And reconciliation takes a lot of effort, takes a lot of work, and a lot of correct measurement points, and a lot of operations don't necessarily do it very well. And I'm just talking about tons and grade, right? You're an iron mine, and you're looking at iron, and you're looking at tons. In some cases, alumina and silicon, phos, and things like that as well. And those simple variables don't get done well in a lot of cases. So one thing I think that could be a big improvement for a lot of the places that have had taken the step to create the geometallurgical model and using that to optimize a value, use it in NPV, use it in planning, is to make sure that there is a feedback loop so that the information can be captured, can be tested and fed back into the model. You know, there's nothing better to tell you about your ore body than when you mine through the darn thing, right? Going out and drilling one little hole that's about that big down for a kilometer and assuming that that is the same thing over 50 meters by 50 meters by something, that's not that great compared to when you mine through the whole bloody thing and you can start to extract that information, right? And it might be in some bigger chunks or whatnot. But yeah, you know, I guess the way I look at it is that across the globe, a lot of operations are, in the last decade or so at least, have dipped their toes in geometallurgical models. Some are doing it very well, some are kind of half-heartedly doing it. But what I haven't seen is the ones who really do a good job of getting the reconciliation part. And I see that just being a natural maturity of this process, I guess, as you go on. The value of that gets more realized, therefore more resources get put on it. Therefore, it starts to become part of regular reconciliation. You know, like I said before, reconciliation is hard on a good day using very simple variables. It gets really complicated with geomet.
I'm aware that some mines have thousands of variables for each block. Sounds like over the top, not to mention costly. Do you have any comments?
Yeah. I mean, this comes down to, is it useful, right? And in some cases, you could argue that it is. With the geometallurgical variables, a lot of times it's not something just simple like, oh, it's gold. Gold, one variable, there you go, bam. It's a combination of multiple variables and combinations of different materials at different sizes. So going back to iron ore, we look at lump versus fine, maybe versus ultra fines, the properties of those. So you break, you know, for every kind of analytical test you have, now you've got that 3 times over. You look at the metallurgical variables of those 3 types of grain sizes, and that starts to get exponential pretty darn quick. And you can see where these things have these very bulky models that have, you know, 100 variables, that this one feeds into that one and it feeds into a regression equation, which then applies this analysis. And usually there's some rules of thumb and there's some fudge factors and they get something out and that gets fed into a recovery and so on and so forth. Yes, it gets pretty challenging and pretty difficult. There's nothing to say from a housekeeping and a management point of view that these models can be kept separate. You know what I mean? That some of these things can be done outside of actual mine planning software. Since a lot of cases, the linear estimation, the regression, or the calculation of these combination of variables into a new variable is just simple maths, right? And you can do that outside the block model as not to clog it up for geologists and mining engineers and mine planners. But ultimately, you want something that's useful, that comes back and gets fed in, that hopefully has a decent audit trail that all makes sense, that you can understand if there's errors, that gives the mine planners something or a limited number of variables that they can then use to assign value to a block.
How does OK work well with geomet variables estimation? However, these variables are non-additive.
Yes, the non-additive nature of the geomet variables is an absolute challenge. So this is a lot of times why you have to take it outside of kind of traditional estimation and look at you know, applying regressions, applying equations that are come up that are derived from a whole lot of metallurgical testing. It would be great if you could take a hard rock and a soft rock, one that's at 1 hardness and one that's at 99 or 100 hardness, put them together and get a volume of material that is 50. But unfortunately, in a lot of cases, it does not quite work that way, right? Go back to that GOL Pilbara iron stuff. If you just take a little tiny bit of this glumpy, clay-rich material, it doesn't take a whole lot of that to clog up trucks and clog up screens and belts and everything else. And through trial and error and a lot of testing, they were able to come up with like a blending strategy, right? It was almost like a cookbook type of thing. And sometimes you have to go down these measures where the practicality of it, or the, you know, being a bit more pragmatic on it and saying, you know, we're going to treat it as, you know, 2 scoops of this and 1 scoop of that and a scoop of something over there, and you mix that together, and what you got now, the mill can handle. Now that works for a little bit of time, but you need to take an understanding of why that is, right? And that's where the Mets can come in, the geologists can come in, people who are specialized in mineralogy material characterization to kind of understand those sorts of things. And again, with the non-additive nature of some of the geometallurgical variables, to me, this is a challenge back to the geostatistics and estimation folks out there to be able to say, you know, what can we do with this? Is there opportunity for transformation of data, of additive data, of getting it into some type of form that then linear estimation, relatively simple linear estimation, can be performed and then back transformed back out? You know, I have no doubt that that is being done in cases, and a lot of times I don't necessarily see that step happening, but yeah, that non-additive nature is a problem. But again, I would go back to taking that step from the other side of the room and say, can you get good information out of it that then is useful, right? And it may turn into semi-qualitative, a ranking system, or a lot of assumptions put on, or things of that nature. But yeah, it's certainly an identified problem that a lot of folks have to deal with.
I hope I haven't missed anything. Thank you so much. Great talk. I'm a recent graduate in Bachelor of Earth Sciences in Mining and Environmental Geology. I've found out that getting into the mining industry is difficult. What advice can you give in order to attract potential employers in the industry?
Network. I mean, get your name out there, talk to as many people, reach out to people. You'll find the people in mining to be some of the most approachable, kind, passionate, nicest people in the world, right? I'm not talking about financiers, right? I'm talking about the technical guys. You know, when you can talk to a Met who loves metallurgy, about metallurgy, and as a geologist, come to them and say, man, I really want to know more. Like, tell me something. They will gobble it up. Just like if anybody comes to me as a geologist and say, hey, I don't know anything about geology, I want to learn more, I'm happy to talk their ear off about these things. And you'll find people across the globe, across this industry, willing to do that. It can be a tough nut to crack into. Network as much as you can. If you're a student or a recent graduate, conferences, talks, things of that nature are usually very forgiving to students from both a cost point of view. There's usually scholarships, opportunities to do field trips, all this other stuff at reduced cost. Take advantage of that. If you've got good connections with your old professors in school, the alumni network at your school, things like that. I mean, right now during COVID crisis and the pandemic, obviously everything is even more difficult than it normally is, you know. But what we have going for us right now is we have relatively robust pricing across most major commodities. There's some that are down, there's a lot that are up. Mining is still going pretty strong. As far as COVID-related industry, we're doing quite well globally. And so there are jobs out there, and there's always people willing to talk. So I'd say just don't be shy. Reach out to people, even if you don't know them personally or whatnot, and just ask them for advice. Ask them, what can you do to maybe help out on a job? How do you get some experience? Things of that nature. So there's a lot a student can do. It seems really intimidating, but like I said, people are nice. And the worst thing they're going to do is say, sorry, I don't have the time. Well, that's not so bad. Feelings aren't hurt. So find somebody else.
That's some great tips. And congratulations on graduating. That's exciting. Do you agree with using one value for recovery for all of the blocks during pit optimization?
One recovery value. Well, I guess the point of the geomet domains and the modeling is that you have the ability to apply variable recovery based on those different domains, right? And depending on cutoff grades, depending on feed, and depending on mine plans, that recovery could be very different, right, of what's being put in and what's not. So I think that's one of the things with geomet models, is it gives you some flexibility to look at variable cutoff grades and optimization of cutoff grades on how that affects recovery. You know, trying to get the most juice out of the squeeze as it is, right? And at some point you can't, and it doesn't happen. So, you know, if the mining engineer can handle variable cutoff grades, and that can be a big challenge, you know, it's certainly encouraged to look at optionality, especially if it's early days studies, right, of where things can go and where your project may get the most value. A lot of times in reality, I see a mining engineer and they want to know a recovery number. If you got zinc, they want to know, here's my head zinc and here's my recovered zinc. But if they see those two things, there might be volumes of information that fit between those two that go on in the background. So, you know, getting that mining engineer engaged to those optionality and that understanding of what goes into it is certainly part of the process. So, yeah, I guess I'm not sure if I can answer that one any better.
The 3D domains identified and the structural model of the area have great influence in the process of estimating the mineral grades. In your experience, how does it complement and what impacts does the structural model have on the determination of geometallurgical models? Tongue twister at the end there, sorry.
Oh, pardon?
Oh, it was a tongue twister at the end.
Oh, yeah, no, understandable. So if you've got your geology and your structure, your lithology, your alteration, your grade distribution, mineralization worked out first, which is usually what happens from an early day exploration point of view. Not saying it's perfect, but you've got at least a conceptual model and some type of model with some amount of certainty associated with it, especially for reporting a resource. That's where it's a good place to start, because that gives you sort of that framework of understanding, okay, well, how does the interaction of these different geological and structural geology elements work into the physical properties of the rock, the nature of the rock, changes in chemistry, changes in mineralogy. And I'll go back to the example before of where you look at a structure, and you know, structures are where you get influx of fluids. And you get influx of fluids, it could be silica-rich fluids, it could be silica-depleting fluids, it could be sulfide-rich, I mean, there's a whole lot of stuff that could happen. If it's heat, you're going to get alteration. If it's you know, acidic, you're going to get alteration. So understanding where these things are will help to pull together how these domains look. In the presentation, I mentioned a lot of times geometallurgical domains are a combination or a subset of those geologic, structural, geotech domains in the first place. So it's a lot easier if you've already got kind of the puzzle pieces around and understand, is just trying to understand how those puzzle pieces fit together in the geomet perspective, as opposed to trying to do it the other way around.
Great. Do you agree that metallurgical groups should be simplification of geological domain?
Maybe not a simplification of it. I've seen geologic domains that are subgrouped into multiple geomet domains, and then the opposite, where you have you know, volcanics, and you've got intrusives, and maybe you've got clastic sediments that are all together. But then the mineralization comes in and cross-cuts all of it and could care less what that host rock is. And it doesn't make a bit of difference because there's no interaction because of the temperatures of emplacement and the chemistries of emplacements and the pHs of emplacements. And what you have would be almost like a large, and I'm thinking about like pegmatite dikes in like spodumene lithium and tantalum and these other type of deposits, where they can come in and the metallurgy is really focused within that intrusive body. But if it's hosted in rock A or B or C, it doesn't matter. So from a geologist perspective, you know, you might need to work these things out for waste rock characterization and environmental and for density and tonnage factors and da-da-da-da-da. But for metallurgy, none of that stuff even makes it to the mill, so they don't care. So it does go both ways. It's not always a one-way street, that's for sure.
Great. I haven't seen anything else come through. You're welcome to jump off mute if anyone else has any more questions for Erik.
Some good questions so far. I really appreciate it. Sounds like there's everybody's brain's getting a bit engaged, and so hopefully there's some items that you recognize from the presentation that you go, oh yes, I've had that problem before, or wow, okay, maybe that's a good idea, maybe I can implement that, or at least one takeaway that this time, you know, you can sock away in your brain, or a little post-it on the wall or something like that. that will help you either in your day-to-day work or at your operation or something. So it's always good it's good for me to have a chance to share this. I always find anytime, whether I'm listening or giving a presentation, it's always something to learn.
Definitely. I'm just giving up. I haven't seen anything else come through. I think. Joe, did you have something? Oh, he's waving.
Oh, taking off. Thank you, Joe. Appreciate you attending and listening. Good luck with the quantum physics.
Great. Well, I think that's it then.
Excellent. All right. Well, thanks everybody for the time. I really appreciate it. Anybody on here, do not hesitate to reach out to me. The last slide of my presentation has got a couple different ways to contact me. Email is always the easiest because no matter where I am, I'll get it. But there's a few other ways on there as well. But yeah, if there's ever questions or something I said that you don't agree with, or you want to add to something, let me know. I find this is the best way to start to collaborate and really grow as an industry, is just sharing information, sharing stuff we've seen, finding out other people's problems and issues, and maybe there's something I've seen that I saw a solution that could help you, or vice versa. So like I said, don't anybody hesitate. Thanks everybody for the time. I certainly appreciate it.
Well, thank you. You've been very generous. This session has been recorded, so once it's available, I'll have it up on socials and on the GeoHug website. So it's just geohug.rocks. So there's heaps of sessions always getting loaded. You're welcome to register anything you like. And yeah, I'm putting a lot of the recordings up there as well. So thank you so much, Erik. Really appreciate that.
All right, well, everybody have an excellent day. Thanks again, and take care.
Thank you.
Bye-bye.